Okay, we're going to start biology talking about a problem solving technique that you've probably already heard about and studied about in several courses in grade school. It's a scientific method. We like to break up the scientific method, this problem solving method, into several steps. The first step of the scientific method is observation. It looks like I spelled it wrong here. So you observe something of interest in the world around you, the material world. It could be the world inside you. It could be like, oh, my finger's really sore today. What did I do? How did I hurt that finger? So it could be anything that our senses perceive. Okay, the second step would be after you observe something of interest, you say, well, what caused that? Or why is that happening? So you ask a question. Now, in asking a question, you're thinking of a possible answer to that question. So, first of all, maybe you ask somebody about, well, why is that happening? Why is my finger hurting here? Or you can look it up on the internet. You can Google it. You can do a background research in the library. So that would be your third step. Look for an answer to your question. Someone else might have an explanation, a good explanation. Next step would be to if I don't get an answer to my question, is to think of a possible answer to my question. Why did that thing happen that I observed? What caused that thing to happen that I observed? So I come up with a hypothesis, a possible explanation. So, for example, a recent use of the scientific method that I used at home was our bathroom sink was clogging up. So I thought, well, what could be causing this thing to clog up every couple of weeks? And so, I mean, I poured hot water. Maybe it was like the soap and the shaving cream, and the face creams that my daughter uses. Maybe that was just building up. So I said, well, maybe if I pour hot water down the drain, it will dissolve that oily kind of soapy stuff and unclog the drain. So there's my hypothesis. If I pour hot water down the drain, then it will clear the clog. Notice how I phrase this. If, then, that's how you always construct hypothesis. If this happens, then this will follow. That if then format is how you phrase a hypothesis if you're a scientist. Okay, the next step is actually test your hypothesis. A test of your hypothesis is called an experiment. So, in my clogged drain example, when I poured hot water down the drain, um, to see if that would clear the drain, then um, that would be my experiment. A very simple experiment. Now, when I did that, it didn't do anything. It didn't do anything. The drain was still clogged. I even used water that I boiled on the stove. So the drain remained clogged. So what happens, I'm in the analysis phase of my experiment. Okay, so what I'm going to do is go back to the drawing board. I state that my hypothesis, my original hypothesis, that there was buildup of non-soluble residue that could be dissolved by hot water, was proven false or incomplete. That is called a null hypothesis. Null means nothing. So the hypothesis has been disproven by my experiment, and I will go back to step 4 and construct another hypothesis. Okay, so what I did was I thought maybe there's something that doesn't dissolve in hot water that's clogging it up. So I actually went back to step 1, observations, because what I did was I opened up the cabinet underneath the sink and I looked at that, where the pipes were, and that little trap that looks like a U. It had 2 screws on it. I mean, 2 nuts on it that I could hand loosen. And I took that thing off. I looked inside of it. Maybe I thought junk got stuck in there. And so I did that. So I just showed you that I went back to the beginning of the scientific method. I did a new observation. I constructed a new hypothesis. If there was stuff that didn't dissolve in hot water that was stuck in the pipe, then that was causing the clog. And then I tested my hypothesis by undoing those nuts and taking the pipe off. Now, I got another null hypothesis because I looked in there. It was kind of scrungy, but it wasn't clogged at all. And so there's another null hypothesis that occurred. So I went back to the drawing board once again, and I observed that this little thing that you could pop up and down to close the drain, you know, that little thing, the drain stopper, I disconnected it from the back. Under the sink, there's a little clamp on it. I disconnected it, and I popped it. I took a screwdriver, and I popped it out from underneath, because this U thing was off. And when I popped it off, there was dental floss clogged around it, and hair, and all kinds of mold. So my new hypothesis was, if I remove the dental floss and the hair from the stopper where it was all clogged up, that would clear the drain. Or I could say, if there's hair and dental floss wrapped around and gunk wrapped around the stopper, then that was clogging the drain. So I pulled all that stuff off. I did an experiment. I pulled all that stuff off. I re-put it in. And turned on the water. Well, connected the U pipe. Turned on the water, and voila. It drained very easily, very quickly. So I tested my hypothesis with an experiment. And now I accept the hypothesis that it was insoluble junk that wouldn't be dissolved in water that was clogging the drain. And I report my results. I didn't report them, I just described them to you. But if I had a blog page and I wanted to help other people, I could tell them that's what I did, and I would be communicating my results to other people, and they could test it out on their own. Now, scientists, when they do experiments, they communicate their results in lectures that they present to the scientific community, maybe other teachers at their colleges, or they publish it in a scientific journal or magazines, professional magazines that professional scientists and students read. What happens then is, if it's interesting to other scientists, they might check your hypothesis out and to see if what you came up is valid. If it isn't valid, they will communicate that in another journal article. This is why the scientific community is regulated by other scientists. You can't just make up something and say, oh, I'm going to publish this fake result and become famous. Because other scientists read it and then say, what? And then they prove that you were wrong. You could lose your credibility as a scientist, your reputation. So if these guys reading your paper in the scientific journal question your results, they're going to try to do your experiment just as you explain it, as you described it. And if these scientists don't come up with the same result, they will write another paper describing their findings, and they'll probably also think of another hypothesis and do another test and analyze those results and re-report the results to the scientific community. Okay, so this is how science regulates itself. So you're not just going to get bogus, imagined explanations of the outside world, because scientists have this self-criticizing system that advances scientific truth rather than keeping it as a pool of untested opinions. And if your hypothesis is an interesting one to other scientists, interesting in the sense that it can explain other questions, that similar questions, and it may become what we call a theory. A theory is just a tested hypothesis that has been accepted by a scientific community and is interesting to many scientists in the sense that it explains all kinds of other things, not just like, why is my sink clogging? I mean, it could be a theory that goes from my sink clogging to arteries clogging, arteries in our body, leading to heart attacks or strokes. If that theory lasts for a long time and is proven in many different situations to be true, it may even become a law, a scientific law. Now, it's important to know that a scientific law can eventually, I mean, there's always a probability that a law can be shown to be false under certain conditions. So scientific laws are proven, but there's always that little backdoor clause that, hey, this law could be thrown out or changed with new experiments and observations and hypotheses. So a law is not absolute. It can change. A scientific law can change, just like a human law can change. So I'm just going to move on through these pages and just kind of review what I just talked about. Okay, scientific method is a process. I just step-by-step process. It doesn't have to follow those steps, but usually that's the order that you do problem solving. Okay, the whole process is to find answers to questions about why the world around us works like it does. Again, scientific method isn't a robotic method. You got to go through each of these steps. But any problem solving method basically has to go through these steps. Maybe you skip a step, or you do it automatically in your head, but they all start with observations, then a test of an explanation occurs. Okay, so hypothesis is an educated guess as to why something's happening, something that you observe. It's a possible answer. It needs to be tested by an experiment. Remember, it's always an if-then format. So here's a generic grade school science project kind of exemplifying the scientific method. Okay, so I guess the student thinks, well, I know plants need water, but what if I enhance the water? Will that make the plant grow quicker? So I don't know why he picks 3 different sodas. Maybe Coca-Cola, Sprite, Dr. Pepper. And then he or she waters the plant with 3 different plants, right? We'll talk about this coming up. One plant with Sprite, one plant with Coca-Cola, and one with Dr. Pepper. Then he measures how much the plant grows, like during a period of a month. So his hypothesis would be, if I water a plant with Sprite, then the plant will grow the fastest. This would be followed by the actual experiment like the picture shows. Okay, so information gathered during an experiment usually it's numerical. I mean, something that you can measure that is organized in a data table. You know, it could be like a spreadsheet like this. Um, and then that data is made visual in a graph form. When it's in a graph form, it's much easier to see patterns. And the patterns can be used in our analysis of whether our hypothesis has been nullified or proven. Now, data can be qualitative as well. Qualitative means you're just describing something. Like if you're doing an experiment and the color changes, I'm not going to use numbers to explain how the liquid turned from blue to pink. So that's like a qualitative measurement or data. Quantitative is using numbers involving measurements that require numbers. So a lot of people think that is just numbers. No, it could be qualitative, especially in biology when you're observing animals and how they behave. Horizontal axis. Okay, just a little bit about bar graphs. Bar graphs, like any graphs, have an x and a y axis. The x is the horizontal. The y is the vertical axis. Right here, the first bar graph we have is kind of weird because they have like the x-axis going this way and the y-axis going this way. Okay, the y-axis is always numbers. See, the y-axis would be like percentages on this one. You can see these numbers going. So this would be like 0%. 100% is right here. And right here on the second graph, numbers of students would be on the y-axis. Okay? So the x-axis is the types. Or it could be dates too. It could be the dates. So the x-axis has a time period or what is being measured. In both these cases, what is being measured is in the x-axis. Now, notice that all graphs should have a title at the top, the categories, or time. If it's that kind of graph, is labeled on the x-axis. The numbers are labeled on the y-axis. Okay, so very much like bar graphs, we have line graphs. And the x-axis will always be for the time period. So you can see the x-axis here with days, and the x-axis down there for days as well. The y-axis is numerical too. It's some other thing that you're measuring besides time. It's something that's varying with time. In this case is the temperature. In this case is the facts that I got right on a quiz or something. Okay, so we got two sets of numerical or quantitative data that we're comparing in a line graph. Okay, here's a review of the scientific method, except this shouldn't go back unless you have a null hypothesis. This shouldn't go that way. It should go off to communicate your findings, your hypothesis to other people, your tested hypothesis. Okay, so it's important in a hypothesis, in an experiment, to identify variables. Variables are things that could change, factors that you can measure, and factors that you can change. So there's three kinds. Let's talk about a controlled variable. Controlled variables are held constant in the experiment, during the experiment. You don't let it change. All groups, okay, when you're doing an experiment, you, like for the plants that you're testing, Sprite, Coke, or Dr. Pepper, the controlled variable will be you have to have the same plants. You have to have the same soil, maybe even the same pots. You have to have them in the same amount of sunlight, hours, daylight hours. You have to have them at the same temperature. Okay, so those are all controlled variables. They're held constant in all the different experimental groups. Okay, all the groups in every experimental group in an experiment has to have the same controlled variables, or else you won't be able to show what factor is causing a change. For example, in this experiment, what if we had one was Sprite, two was water with Coca-Cola, and three was water with Dr. Pepper? So what if after 4 days, the Sprite grew like that, Dr. Pepper grew like that, and the Coca-Cola grew like that, and the Dr. Pepper really shot up. Well, if they didn't get the same amount of sunlight, maybe Dr. Pepper got more sunlight than the other ones, then you can't say that Dr. Pepper was the cause of the increased growth in the plant. So it's very important to control variables. Okay, independent variables are factors that are changed by you, the experimenter. Independent variables changed by the scientist, or it's the time that passes. So it could be either one, depending on what type of experiment you're doing. So, independent variable for the Sprite, Dr. Pepper, or Coca-Cola experiment would be the type of soda that you're watering the plant with. So, a graph would look something like this for that. So you put your category, by the way, the independent variable is always on the x-axis. So if I were to plot my results from my soda experiment on the plants, I would have here a category for Coke, I have a category for Sprite, and I have a category for Dr. P. And these would be the the independent variable, the thing I'm changing, the type of soda I'm changing. So that's the x-axis. The y-axis would be the increase in the height of the plant in a certain time, let's say in a week. So what kind of graph did I just draw? I drew a bar graph, right? This graph, the effect that the sodas had on the height of the plant. That graph I just showed you, the dependent variable is the thing that might be affected by the change in the independent variable. So you saw the bars were different heights in that previous graph. Okay, so they always go on the y-axis. So one of the videos I show you has D dependent on the y-axis and independent on the x-axis. So just think of the D. You make that piece of the D is up and down, and the I has the horizontal parts, which would be the x-axis. Okay, so I have two other little examples down here. If I had plants and I was seeing the effect of light on the plants, I could on the x-axis put how many hours of daylight the plant, a given experimental group received, and then I could measure the height after 10 days, or the difference in the height after 10 days from the original height. Okay, so the dependent variable would be the height of the plants, and the amount of daylight that they got would be the independent variable. So again, independent variable is what the experimenter changes, and the dependent variable depends on, supposedly, the independent variable. So the height of the plant depends on the hours of light that it received. Okay, again, here's another example. Force to throw, distance of flight. So let's say I have a paper airplane, and the harder I throw it, the farther it goes. So the force that I apply on the airplane is the variable that I, the experimenter, am applying, manipulating. That would be the independent force. It should go on the x-axis, and how far the airplane goes, or it could be a baseball, how far the airplane goes with that force depends on how hard a force I apply. So the distance that the baseball achieves is the dependent variable, whereas the force that I put on the ball is the independent variable. So it's very easy to identify, given a graph, even if you don't even know what the graph's about, what independent and the dependent variable are. The dependent will always be the vertical. The independent will always be the x-axis. So in this case, the independent variable is the hours that I used to study for the test, a student used to study for a test, And the dependent variable is their grade. So supposedly this graph shows that, what does this graph show? Interpret this graph. Well, the more hours I spent studying for the exam, the higher the grade I got on it. People got on it, not just me. There's each of these points is an individual student. It's hard to control the control factors, but I'm assuming that all these students had about the same control factors, which is kind of unreasonable. Okay, so in that previous example, I'm assuming that every one of those students got the same amount of sleep, that they had the same amount of distractions when they were studying, they ate the same nutritious meals, they they weren't exhausted from practice, they had the same amount of exercise, etc., etc. Now, when you're running an experiment, you should have a control group, or just a control. A control group will not get the independent variable. It will not get the treatment. So if you had a medical experiment and you're testing out a drug, how effective the drug is in relieving muscle aches, let's say. Okay, so what you do is you have people that you give a fake pill to, or a fake treatment. They don't know it's fake. Okay, we call that placebo. And then you give other people like 1 milligram of the drug. You give another group 2 milligrams, etc. Okay, so in increasing amounts, like, okay, this group right here is called the control group. It did not receive any independent variable. The other ones received the pill or the ointment, and it looked the same as a placebo, but inside was the drug that they were experimenting with to see which one was most effective, if anything, on muscle soreness. Okay, so the control group did not receive the independent variable. Okay, I would probably do a graph then, showing the results. On the scale 1 to 10, I would ask the people, how's your muscle soreness compared to before you took the drug? And then I could make a graph and then see what the best dosage was. But without a control group, I couldn't accurately say that the drug relieved that muscle soreness. You need a control group to compare the results of the experimental group. These guys are all the experimental groups. So if the control group felt relief, and let's say they felt relief equal to what one of the experimental groups felt, you couldn't say that the drug was effective. Okay, I'm going to give you some experiments, specific experiments, and you're going to identify these terms, apply them to the specific experiment, just to check your understanding. Okay, so pause this and take some time to read this, and then come back. Okay, the independent variable. That's the thing that's being manipulated. What variable is being manipulated by the experimenter? The type of fertilizer. Fertilizer A or fertilizer B. What's the dependent variable? That's how that's the average growth for each type of fertilizer. So that's the growth. Basically, that'd be measuring the height of each plant. What's the control group? That's the plants that did not get any treatment, no fertilizer. So it's a plant group with no fertilizer. What's the experimental groups? Well, the ones given the plant groups with fertilizer. The conclusion is, after you do an analysis of the experimental results, that's where you explain whether your hypothesis has been nullified or verified. If it has been nullified, you'll probably want to go back and think of another hypothesis, run another experiment, and then do another conclusion. So these researchers are seeing how the students' ages affect the time it takes them to complete a puzzle. Okay, so ages. Which one's the independent variable? Which one's the dependent variable? This one I think of, what depends on what? Does the student's age depend on how long it took them to put the puzzle together? Does his age depend on anything? No. Does how long it takes to put the puzzle together depend on the student's age? Yes. So let's write that. The puzzle solving time depends on the age. Age doesn't depend on puzzle solving time. Of course, you can't manipulate the age of the subjects being studied here. So the puzzle solving time is the dependent variable. And the age is independent. Okay, so keep it straight like that. It's kind of confusing, I know. So I would put the puzzle solving time as the dependent variable. And I put the age as the independent variable. Kind of confusing. Now, you might say, Mr. Noyes, time, you're always supposed to put the time on the x-axis. Well, age is like time. We have kind of two times going here. The time to solve a puzzle and the age of the kid. So you can't just memorize, the time thing always goes on the x-axis. Okay, so here I just explained again what we just talked about. What would be the hypothesis? Well, putting the if-then statement. If the student was older, then theoretically he would solve the puzzle quicker. Now, there's going to be outliers. Some kids are going to be really good puzzle solvers in early age. But you should see a pattern that kind of goes like this. Age, puzzle solving time. So as age goes up, the puzzle solving time goes down, right? As age goes up, the puzzle solving time should go down, with some outliers maybe. Here they're talking about constant variables. Well, you give each kid the same puzzle, 30-piece puzzle. You don't give one kid a really hard one with more pieces or a harder picture to solve. Other constant variables, same location, whatever. Is there a control group here? No, you really don't need a control group. How could you have one? So here's another experiment, like a physical science experiment. If you have a wire and you connect that wire to a power source like a battery, electricity will flow through it and produce a magnetic field. You can strengthen that magnetic field by putting a nail through the coils. Now, first of all, this wire needs to be coated with plastic so that the charge doesn't leak out or short circuit. Okay, but they didn't say that. Anyway, so different size nails were used. Okay, so here's a big nail and here's a little nail. The number of paper clips the electromagnet could pick up was measured. So you can see this guy picking up. Here's a paper clip right here. And he's seeing how many paper clips he can pick up at one time before they fall off. Okay, so now, I'm going to ask you the question. What's the dependent variable? Okay, so ask the question, does the nail size depend on the number of paper clips that you can pick up, or does the number of paper clips you can pick up depend on the nail size? Which one makes more sense? Well, nail size does not depend on the number of PCs it can pick up. The nail size is independent of the number of PCs it can pick up. But the number of PCs that it can pick up depends on the nail size in the magnet in the coils. So the dependent variable is the number of PCs. And then the nails are independent variables. Because the size of the nails were changed by a scientist, by the guy doing the experiment, they are the manipulated variable, or the independent variable. Maybe another hint would be manipulated for independent. And the dependent variable depends on the size of the nail. Okay, so controlled variables. The voltage of the battery, the type of wire, the length of the wire, the material of the nail. None of this type was changed. It was just the size of the nail that was changed. So you can see there's a hypothesis here. If, then, if I use a heavier bowling ball, then the ball will travel faster down the lane. I don't know about that hypothesis. It's going to be hard to make it go faster down the lane. But anyway, what am I changing? Okay, what depends on what, according to this hypothesis? The weight of the ball depends on how fast it will travel, or how fast it will travel depends on the weight of the ball. Which one makes more sense? The weight of the ball has nothing to do with how fast it travels. How fast it travels depends on the weight of the ball. It's not really obvious, but the control variables, you got to assume that the guy's going to apply the same force on either ball. So the force that he throws the ball, the push that he gives the ball, has to be the same to do this experiment right. So that's the control variable. Okay, I guess the hole size, it better fit his hand. All these different weight balls better fit his hand, the holes in the bowling ball, the same way. Okay, so you could do that. The experimenter is changing the weight of the ball and then seeing how that affects the speed. So he's kind of wondering, does the weight of the ball affect the speed? Okay, the speed is a dependent variable. The weight of the ball is what he's manipulating, independent variable. So the weight would be down here, and the speed of the ball would be here. So for a given force, the bigger the weight, the what the speed, I would get a graph like this. Okay? So as the weight goes up, the speed for a given force, pushing force, goes down. Okay, so I'm going to check out what brand of paper towel does the best quickest at absorbing water. So pretty easy. Does the brand of the towel, the brand of the towel is what I'm manipulating. So that's independent variable. The amount of water that is absorbed per minute, I have no control of that. That's an effect of the type of paper towel I'm using. So the manipulated variable that I'm making is the brand of towel. And the brand of towel depends on the amount of water absorbed per minute. So I would put the independent variable here. This would probably be, there's my 3 brands of towels. This would be the amount of water absorbed per minute. So how about grams of water dissolved, absorbed, not dissolved, per minute. Okay, so what's the controlled variable? Controlled variable, well, it has to be the same kind of water. I guess you dip it in the same, you put the same amount, you keep the same amount of the paper towel in the water, like a corner of the paper towel in the water, or the edge of the paper towel for each case. What else? Temperature of the water. Okay. Okay, once again, here we go with the amount of daylight given a plant in its growth. So the amount of, I'm manipulating the amount of light that the plant gets. So that'd be the location of the plants. And I put that on my independent variable axis, which is the x-axis, and the height of the plants depends on the amount of light it gets. So I put that on my y-axis. So obviously, this would be, I'm not doing time, amount of time, I'm just doing location. So obviously, the sunlight one will grow the fastest, and I would use a bar graph because I have categories. Okay.